I'm going to talk about building languages for self-rebuilding robots. That was sort of a nice combination, and we're doing both. I'm from the University of Southern Denmark, and of course, I mean, this is about robots, and robots is hardware and electronics and software and AI and all kinds of other things together. It takes a team. So there's a whole bunch of people who are involved in this and have some names up there of other people as well, but it's a big team effort. But before I begin, here is the standard default reminder. So please remember. And moving on. So I loved the keynote this morning. I mean, that was just amazing, right? And we should have more of that. I don't have anything that's anywhere as cool as that, but we have in fact been very inspired by some of the same scenarios. So, and here's the question, right? So as we learned this morning, you can only bring a limited payload. When you go to Mars, it's very expensive per kilogram. So if you want to bring a robot, which one do you bring? Do you bring, well, there's of course Curiosity you can bring along. It can go scouting and do scientific missions for you, so you don't have to go outside. Of course, I'm thinking, you're going there in person, right? So we could bring a rover like that could go scouting for us. Or if we're worried about the terrain, so of course a rover has wheels, so due to its physical properties, it's going to be very efficient when moving across flat terrain, but it will have difficulties in more difficult terrain. So we could also bring a walker kind of robot. If you haven't seen the Boston Dynamics, now Google Big Dog robot that runs around with sort of very natural movements, see the videos, they're amazing. So we could also bring that and have that running around on the surface of Mars. Or maybe if we're actually building a habitat and we're going to live there, then maybe we should be bringing an industrial robot around. Well, industrial robots, as you probably know, are key to industry in Europe and in many other Western countries at the moment. They're building lots and lots of things. And of course, when we go to Mars, we will need to build things. And we probably don't want to go back to having the hammer and saw and doing everything by hand. So we might want to bring the industrial robot. But we only have limited space, so which one do we bring? So who votes for bringing Curiosity around for scouting so we don't have to go out of our habitat? But we can only scout flat areas. There's one vivid, timid vote there. OK, so how about Big Dog? Because let's have that running around on Mars, right? That would be cool. OK, yeah? OK, and then the industrial robot to build all the stuff that we need so we can actually survive. Survival, OK. All right, so, and of course, this is actually a picture. I haven't had a chance to see it yet. It's coming out just now. This is a picture from The Martian. So there's this guy who goes to Mars with some other people, and something bad happens. And the problem is, when bad things happen, you don't always know it in advance what's going to happen. So maybe you didn't bring the right robot for the bad thing that would happen. So my answer, this is of course cheating, is that, oh, we shouldn't bring any of these robots. We should build a robot building kit, so we can build the robots that we need when we are on Mars. The video here on the right is 3 times normal speed, by the way. A lot of our robots are very slow, so I sped up most of the videos to make them look more exciting. So these videos are from a competition that we've competed in a couple of times. You bring a suitcase of robot parts, a small suitcase, and then you have to solve tasks. You don't know in advance what the tasks are, and they all have this Mars-like emergency scenario. You have to solve things outside. And then people are building all of these weird contraptions. I mean, they're taking different robot parts, putting them together, and some wood, and some tape, and some string, and whatever else you have available to try and solve the problems. And you have a couple of hours to build robots, and then they have to go out into the arena and do things to gain points. And this is a great sort of like a massive hacking experience. And but except, of course, when there's only 3 hours, you don't have so much time to code. It just takes so long. I mean, and the robot, even building a robot, I mean, all the parts have to be ready. You could maybe use Legos. But usually Legos are not good for building big robots that solve bigger tasks. They're mostly useful for smaller things. On the right here, we actually have, this is a video from, this is our robot that just gained a lot of points, but that was one of the tasks, raising an antenna up into the air. So they're very simple tasks we have to solve. But nonetheless, this illustrates one of the basic principles here that there's a few seats over on the left there. The basic idea is that we have these building kits such that we can very quickly build robots that solve the problems that we have. So, and disclaimer, don't actually really bring these robots that I'm showing you today to Mars, because then you'll die. I mean, they're research prototypes, but they're pointing in a direction that we're trying to go to. And of course, in the context of this conference, what I'm also eventually going to get to is how do we program these things? But first, so this PowerPoint with movies in it is a little bit tricky. Let's be honest here. So, I mean, below, so these are 3 robots that we build ourselves from our robot building kits. It's called the ATRON. I'll talk more about it later. And I mean, I'm a researcher, so I'm used to making up good stories, but there's a bit of a distance from there to there, right? To be honest, so we still have some work to do. We of course need to develop these some more, but on the other hand, if we can, so these robots, I should say, will never be as good as the special purpose-built ones. But keeping in mind this morning's keynote, it was a massive engineering effort to build the Curiosity rover. I mean, it's amazing, right? Amazing piece of machinery. But if we're stuck on Mars and we have 1 hour or 2 hours to build a robot, we have to do something different. And that's the thing we're looking at. Or maybe we're even in the situation where we're not there. Maybe we just send a bunch of robots to Mars and we're not even there to build new ones, but we still want maybe other robots from what we had in mind at first. So here's the special thing about, so this is showing the CK-bot and M-Tran, they're sort of similar. So these are actually, because they're modular, they're built from small pieces of robots that are put together in a bigger one, they can rebuild themselves. So here something bad happened that might not happen on Mars, but something else might happen on Mars, where the robot falls apart. And so who's going to repair it? Well, the robot on the left, CK-bot, in this case, is showing how it can self-repair. This robot here started out as a walker, the M-Tran, and it's going to rebuild itself into a snake robot. So the idea is that, well, as a walker, you can move more efficiently, but maybe it's hard to get through a hole. So you might transform yourself into a hole, do something, and then come back out again. So these are actually transformer robots. And that's what we mean by self-rebuilding robots, self-reconfigurable robots. We have, and we're actually building these machines at the moment, which in one way is amazing. We have self-rebuilding machines. They're not very good yet. I mean, this is not a very good snake robot. If you've seen other pictures of snake robots, well, you can do much better than this. But it is a self-rebuilding machine. Still, I mean, it's incredibly neat, right? On the other hand, we're still a long way off from the robots that we saw to begin with. So I just want to give you a little bit of perspective on where it is we're trying to go with this kind of technology. So the M-Tran here is so useful that it might actually, I mean, you could eventually imagine it might maybe be useful for something. But taking it a bit farther, the long-term perspective, this is like 20, 30 years into the future, is what we like to call programmable matter. Now imagine you take the same principles as before, but made the modules really, 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 really tiny. So that's this, it's a bit hyped, the video on the left, but it has this idea. So this is called the Claytronics project. So they're building, or trying to figure out, what if we made these things be really, really tiny? How can we do that in the first place? This requires completely new fabrication techniques. And how can we program them? I mean, this is a distributed system consisting of millions and millions of nodes, and you have to somehow distribute the control across all of these nodes. I think it'll be a while yet, honestly, before we see something as advanced as that. But they have actually built prototypes, and also some that I couldn't find a picture. Some that they're doing a 2D version to begin with. So this is a two-dimensional version of the same principle, cylinders that can move around on each other using electrostatic forces, or electromagnets here, but if they were smaller, they would be using electrostatic forces. So this is, in some way, what we aspire to do with this kind of technology. We're not there yet. This only works in simulation, and probably will only work in simulation for a while yet. They've been looking a lot at how to program these things. They've been looking at that from the point of view of how to make it work in the simulator, which sometimes lets you do things that maybe won't really work in practice. So in what I'm going to be talking about, we've been doing something different. So we've been working with the ATRON robot, which you can build many different things from it. They're much bigger. One module is about, 2 hands together, pretty big. But in a way, it's not completely unlike the Claytonics you saw before. They're these spheres, they can hold on to each other with hooks. They're difficult to program. So if you look at the video on the left, so this is an initial experiment trying to have the robot rebuild itself. You'll see more about it later. And when doing robot experiments, there's this thing which we technically call the hand of God, which is the robot doesn't do what it's supposed to do, and then someone reaches in and bashes it a bit or does whatever. So here, my student Mirko is desperately trying to get the robot to move, but it doesn't. Programming these things reliably is difficult, and I'll get into more details later on as to why it's so difficult. And the setup we're showing you here is actually just sort of hard-coded random movements, because we didn't know how to program them, such that what we wanted to do was have a sort of fabrication system. So conveyor belts built from the modules, transporting things around. And of course, this is not just a plain conveyor belt. This is a self-rebuilding conveyor belt, so it can adapt its shape to different kinds of things you want to transport around. But even though, physically they're capable of doing this, we didn't know how to program them. And that's what this talk is about. Eventually, I think this kind of technology can be very useful. Bear with me, we're looking into the future, although I will also come up with some practical applications later on. But we first have to learn how to program them, such that they are reliable, and it doesn't take a complete PhD, like 3 years or 4 years, however long time it takes, to make the robot do a new trick. And that's what I'm going to be talking about. Programming robots is painful. And one important message, I think, for you today is don't ask what robots can do for you. Ask what you can do for robots. What I mean is, we have robots doing lots of useful things, but it really needs some good software engineering. They're desperately trying to make better software. And it's not always the right people who are writing the software that runs on the robots. So we as professionals, I think there's a lot of potential in robotics, but it really needs the right kind of people. Because there's lots of bugs, lots of things that go wrong. Hardware partially breaking down, or sensors that are a bit inaccurate, leading to all kinds of complications that we're not used to, but that we have to address somehow systematically. And maybe in a bit more detail, so from the point of view of our system, of the ATRON robot here, this is, honestly, one of the problems is that we build these things ourselves. That's nice, because we have this really cool hardware, self-rebuilding machines, but this is like building your own laptop. By soldering components together, and I don't know about you, if I tried to do that myself, the result wouldn't be very reliable. And that's the problem here. We're pretty good at building robots, but still, it's very hard to get to the level of reliability we're used to with ordinary computers. So that's one issue, and I'll get into a bit more detail about that later. The other thing is that we have some pretty complicated stuff going on. I call it intelligence here. Maybe I should have put some quotation marks on it. They're algorithms. They're whatever makes the robot do what it's supposed to do. And when you have really complicated behaviors, advanced things going on, well, then it's usually hard to come up with a specific algorithm that does exactly what we want, unlike more standard problems in computer science. So I put some neural networks, some genetic algorithms, and some multi-agent systems up there, and whatever else approaches. There are many different approaches to dealing with this complexity, where we don't have perfect solutions, where we don't know exactly what to do. And they're great. But how do you program those things into our unreliable hardware? Well, the standard approach that you take is that you write a whole bunch of C code. And then when the robot does what it's supposed to do, you throw the C code away because you don't want to look at it again because it was awful. And then you write some new C code. So that's sort of what we've been looking at here. And what I'm going to present in this talk is our experience in using domain-specific languages. So making new languages that fit the kinds of problems we're working with as a means to doing this. So you might be wondering, why don't we just use Java or whatever, or some other high-level language? Well, the thing is, our high-level languages don't necessarily run on our tiny embedded platforms. So actually, the ATRON, as I showed you, that's pretty big. And we have actually made some more powerful versions, but they are very limited in resources. And maybe that's not too bad, because we ideally want to go down to the really, really tiny modules. And they're never going to be really powerful. With a lot of this hardware, as computational power increases, we just want to make them smaller and more power efficient. So I don't think we're ever going to be running huge, complicated Java programs on these things. We're going to be running maybe not C code, but something else. Something that takes into account resource requirements, time, and has more modest space usage. And my way of doing that, well, there are different ways of doing it. So some people make up really clever languages and abstractions and whatever, and I think that's horribly complicated. So the way I deal with this is to make domain-specific languages where I can express myself in terms of the problem I'm addressing, and then have it generate some C code, such that I don't have to write it myself. And if I have the right generator, then everything works and I'm happy. Getting the right generator can be tricky sometimes, but that's part of the job. So just to be clear, I'm not going to be doing domain-specific languages for neural networks or whatever, but I'm going to do the languages that those people can use to make the robot do something. And just quickly catching up on domain-specific languages, so I don't know if everyone here is familiar with them. Who here is familiar with domain-specific languages? Good. You should be. So, I mean, I think they're excellent. And part of it is maybe because of the problem I'm facing, because they're really the right tool for the job. I mean, it's very hard otherwise to abstract over the things that a robot does. But being able to make up our own abstractions is really powerful here. And some of the normal advantages that we have from domain-specific languages are perfect here. So we have the issue of how can we get better productivity? Well, it's hard enough already writing programs for robots, so better productivity does wonders. Communication with domain experts is, well, the domain experts here are roboticists, so I mean, they can talk programming stuff, so that's not such a big deal. Change in execution context, that's exactly what I was talking about before. I want to write something high level and get C code that's very efficient out of it. Alternative computation model, well, I'll be showing you a few things where we want to do distributed programs without worrying about distribution, where we want to have programs that run forwards and backwards because the robots need to do things forwards and backwards. And again, it's a completely different way of thinking about the execution. And of course, verification. I'm not going to talk so much about it here in this talk because our robots, verification is interesting because it could help us catch bugs early on. And I'm going to be talking a little bit about some more dangerous machinery later on, where verification is really important. So, just to be clear, so we're talking about how to program the ATRON robot here. So this is a modular self-reconfigurable robot. It's a modular robot, meaning that each of the modules, each of the round spheres is unto itself a robot. It has its own battery, its own actuators, its own sensors, its own computational power. It has a massive 8-bit Atmel processor with 4K of RAM. And this is excellent when you're doing program generation. It actually has 128K of ROM for storing the program. That's pretty good. So, and again, we could put a bigger processor in there, but if we want to go really tiny, that's maybe not what we want. and that is one of our future goals. It does 3D self-reconfiguration, meaning you start with a robot that is built in the right way, because there are certain constraints in how it can rebuild itself, and it can rebuild itself into another three-dimensional shape. Of course, it's still going to be made out of ATRONs, out of round blue spheres, so that is a limitation of the technology, as it is. It can build lattice structures. These are like crystal structures where they're really strong. So you could build very strong, bridges or pillars or whatever, because they can lock each other into a crystalline structure, essentially. But you can also do something like the snake robot we saw before, where it's more flexible and bending and doing things. There are, they use physical connectors. I'll show you a video a bit later where you can see a bit better where they to hook onto each other, and then one module can grab onto one, shift to somewhere else in the structure, and release it again after someone else has grabbed onto it. They communicate with each other using infrared. So we don't use radio because, well, basically this is made out of metal, so it's one big antenna. So radio wouldn't scale so well. So we use infrared for neighbor-to-neighbor communication, which is nice because then we can scale to arbitrarily large groups of modules. It's bad because it turns out that infrared is a bit difficult to work with when you're building machinery that rebuilds itself. So we have this, basically there's a problem where sometimes our communication diodes will be misaligned, and it's not a reproducible problem in the sense that two modules that connect to each other might communicate just fine. Two other modules might not communicate at all, or only have one-way communication, or might communicate to the wrong module because the IR reflects off something. So that makes it a bit more complicated. So we have here a real-time embedded system with a dynamically evolving topology because the robot can rebuild itself. And they're unreliable. There's the infrared communication problem. They also tend to lock up sometimes, maybe because we built them ourselves, also because, well, this kind of machinery is a bit difficult. So if you're not careful when we program them, we easily get into the, I'm trying to remember that Leslie Lamport has this wonderful quote about how a distributed system is a system where a server somewhere that I've never heard of before crashing keeps me from doing my work on my own computer. Something like that. So this is basically the same problem. I mean, if you imagine one of these modules locking up, then we want the whole robot to keep going. That's the whole point. But when we program them, we often tend to make programs where this is not the case, where we somehow become dependent on all of the other parts of the system to work perfectly, not intentionally, but when C is your abstraction layer, well, that's how you tend to end up thinking about things by experience. So we were looking at how to make better languages for this. Well, so we went ahead and made some languages. So here's our first prototype. We're thinking, oh, but these round blue spheres, they're like objects, right? And we like object orientation, so that must be nice. And so each of the, we can program it such that we give each of the modules, we think of them like an object, as sort of like a whole part design pattern. I was very much into design patterns at the time. And so that might be a nice way of thinking about it and making the programming model accessible to the programmer. And so we could write something, some declarations that express somehow how things connect to each other. And we have different roles. So we have the connector in the middle, the axles that hold the wheels, and then the wheel modules. And we can give them different kinds of behaviors. And then we can say, oh, the whole is something like this. So that was our first try. And it was sort of interesting to, well, compared to the C code, that would be like hundreds of lines of C code to express the same thing in a much less clear fashion. So we got modularity, remote procedure calls, distributed programming worked well. One thing that wasn't so nice was that it was actually hard to get the connections right because we had to write them manually. And well, the programming model maybe wasn't perfect, and it actually didn't work very well. I mean, there are all kinds of problems we ran into it with it. So back to the drawing board. So we thought, okay, so object orientation maybe wasn't the right way to think about this. And at the time, I was, well, I've always been sort of interested in functional programming, and I thought, oh, well, lots of people are doing more and more functional programs, so let's try functions. And specifically, we went ahead with this concept called functional reactive programming, which is, it's an amazing idea. So basically, you write your program as a bunch of functions, and then they're continuously recomputed by the underlying system. that seemed to make sense here. So we can write that certain parts of the control is dependent on sensor input, and then that's how it should map the sensor input to the actuators. So I mean, that seemed to kind of make sense. And we could write down the roles as sort of a similar to data types, and write functions. Functions would then be applied across the structure of the robot. And we could have this. So for example, here there's this. So computing the number of wheels, then we fold a function that adds 1 to the current number of wheels across the structure of the robot. We can write these, like functional programs. Sometimes you can write these wonderfully compact things, which is, yes, this is perfect. So that was one of my experiments. So, well, some good things about it. So the roles as a concept here made sense, and we had wonderful functional abstractions, which is nice. And of course, I was telling my robotics colleagues about this. Oh, the wonderful functional abstractions. They were like, no. Because it turns out that not everyone loves wonderful functional abstractions. Actually, going back to, I showed you the Claytronics, the simulated robots. So they were doing logic programming for programming those. And they had actually the same problem. They had this wonderfully compact logic expressions for expressing what a robot should do. But no one could understand them. And, well, they only worked in simulation as well. And it was also hard to actually implement these wonderful functional abstractions. It turned out when we only had basically 2K of RAM free on each module, because the rest was used by the operating system. And it also, one of the good things about these robots is that they can rebuild themselves, which is sort of a more discrete thing, and they were more useful for continuous things. And we couldn't really make it work. So again, maybe not the best. So then I talked to some people who are doing role-oriented programming. So people also talk a lot about roles in terms of modeling and processes. How do we do this? So we thought, okay, let's try and put that in our language. So I have a small video here, and this is the kind of video that you work for 2 years, and then you have a very unimpressive video. So this is one of those. Okay. So, so here we have the robot. There's a bug in our program, and the program, of course, is distributed across the nodes. And then my student Mirko is carrying one module there to reprogram the module. So they're actually being reprogrammed by sending a program message to one of the modules that then distributes a route across all of the other modules. So when we got to the point here where we had a virtual machine running on each of the modules, which I was pretty happy about, because we only had this 2K of RAM available to it, and we could do dynamic updates of the programs that were running there. So that was pretty neat. And the virtual machine worked in terms of roles, so each module plays the roles, and then it grabs whatever code is relevant for that role and executes it. And we also made a small role-oriented programming language, so we could write, the role of a wheel is like this, and it has certain kinds of properties and certain kinds of behaviors, and we could write what events should they react to, how can they communicate with each other. And we could structure the roles into a nice hierarchy, and that was actually feeling pretty good. And people were sort of okay about it when I was talking to my robotics colleagues. Yeah, well, they were already using roles, actually, I should mention. So they were using roles to think about how the robot should be doing things, so that makes sense. So overall, that was pretty good. And we could do small, simple things with it. So we then realized that this worked, but it didn't really solve the hard problem. The hard problem was, given a whole robot made up of many modules, how do you program the robot as a whole? So we're thinking too much about the individual modules, not about the behavior of the robot. And also, I put here doesn't really work because it turned out we were making assumptions about communication being reliable. We didn't really mean to, but you easily get into this. So we were getting into a style of programming where the programmer would say, send a message to the wheel and ask it to do something. If that message was lost, then, well, how do we proceed from there? So again, although I should put it work much better than what we had before, it still wasn't there. And then, there was this insight, which was that we should think much more about having one program distributed across the robot. And this is one movie that I like better. So this is showing, again, the ATRON robot starts out as a car, which could drive around, it doesn't have just, but then it rebuilds itself. And this rebuilding is done using our distributed programming language. So we write one description of what the robot should be doing, and then rebuilds itself. So you can see the hooks moving in and out, and they're continuously communicating with each other. Some operations are done in parallel, and it's actually highly robust in the sense that you could turn off parts of the robot, and when you turn it back on or if you replace the modules, they would just pick up whatever was going on and continue. We're running the program here that changed from a car to a snake robot. So again, this is the case where we're driving around as a car, and then we want to change to a snake robot. So what's nice, although I didn't say that before, what's nice here is that before we made this, there was only one video of the robot doing that, and it took a week to shoot that robot. Shoot that video. They kept going for, I think they wanted to shoot the robot at the end, because they had like 40-something tries to make it do it once. And then they got the video, and they could write the paper about it. Here we actually got a 30 times improvement in robustness. So we did still have a few failures every once in a while, but it worked basically 5 out of 6 times with our new and improved programming approach. So that felt very good. And now we actually, and also, as you can see, we were changing the robot. The robot was changing from the car to the snake robot. No one had actually done the other way before, because, I mean, who wants to spend another week doing that? But our programming language here is reversible. So you can run the program one way to change from car to snake, and then you can run it the other way to change from snake to car from the same description. The description is, I mean, it's not incredibly elegant, but looks something like this, where you can say, oh, this sequence consists of a number of operations that happen across the modules of the robot. And this is then compiled down to a robust execution model, where instead of thinking a lot about the state and what each module is doing, we have more of a sort of a wave of state changes propagating across the robot. They might be changing independently at different parts of the robot, and then they're continuously trying to communicate these state changes to each other and merging them whenever communication is established between different parts of the robot. This is a completely different programming model in terms of what happens when the system executes. We don't assume two-way communication, for example. So if information can get through, it will get through and will be merged into our global state, at least our understanding of the system. This is an example of what we call a spatial program language. So because in this kind of system, it takes time to communicate from one end of the robot to the other. So instead of assuming we have a perfect notion of state, which is reliable and the same across the whole robot, we have a programming model where state changes eventually and will eventually end up being the same, will eventually converge to the same state, but as long as we have enough information to proceed locally, we do. So this was a fairly simple example, but it actually gave us a massive improvement. So just very quickly, one of the key things here is that each module has a local notion of state and then continuously communicates that to all neighbors that happen to be connected. And sometimes we have two-way communication, sometimes we only have one-way communication. And as soon as a module receives information about what happened in some other part of the structure, it merges it into its own worldview and propagates that information to the rest of it. All messages are sent as idempotent messages, and all operations are idempotent, meaning it's okay if you sort of get halfway and you lose track of what you're doing, you have to do it again, and it's okay if messages are sent multiple times. And again, this really did wonders for improving the reliability of this otherwise highly unreliable system. We could tolerate all of a sudden partial failures, so parts of the system that were otherwise we would get locked up when something bad happened would continue working, and we could also switch off parts of the robot and it would pick up again. In terms of efficiency, we were much faster than before. We could do things in parallel. Communication was just going on at the exact rate which was perfect for the robot, which turns out to be around 10 hertz for these machines, but a different kind of robot, we would just change it. That's something which we didn't put into the program, of course. This is part of the compiler, part of the code generator, so it's something the programmer doesn't worry about. And then there's this idea about reversibility. It's sort of the same video again, but that actually got us thinking a lot because, well, in this case, it turned out that reversibility was very useful. So going from one shape to another, it's kind of obvious that you want to be able to go the other way as well. So we started experimenting a bit more with, so what happens if we run reversible programs on a mobile robot, for example? So what is the reverse of going forwards and trying to evade obstacles? Well, turns out that that didn't work so well. But it's really perfect for self-reconfiguration, and a bit later I'll show you an excellent example of where reversibility actually turned out to be useful. So all in all, we actually have a system that works. We have a practical use of this notion of reversible computing, which is that programs can run both forwards and backwards, which otherwise is sort of a highly theoretical computer science construct. The only bad thing here about the language is it only does sequential operations. So we have some more work where we kept working with the language to have a much more powerful language. I won't get into details now, because basically it was about the same principles as you saw here. So perspectives on this. So ultimately what we'd like to do, this is the programmable matter that I talked about before, more for Genesis, building new things out of smaller parts. So we could imagine robot cars built out of ATRONs coming together on the floor, building up a large pillar. So this was a sort of a rescue scenario where you imagine, oh, there's a house that's about to collapse, and you send in your small robots. They form a pillar that then supports the house, or build something else. And the key to making this work was understanding that, well, our hardware has certain limitations, and we must provide a programming model that matches this. We must limit the expressiveness of the programmer such that the programmer can only express things that we can make run in a reliable way on these robots, because otherwise it's never going to work. Unfortunately, we don't have a systematic way of doing this. So this was about making new domain-specific languages. I tried to convey how, well, there are different kinds of abstractions that we're thinking about of putting in there, but that was the insight still, which, I mean, we often know that you're trying to solve some programming problem, and then at some point you realize, so that's how it should be done. And that was sort of the same insight here at the language level. We are trying to find out ways of being more systematic about this. Just like we have design patterns for doing object-oriented programming, we think maybe there are patterns for how to do languages that could help us in doing this. I mean, that's something I personally consider very interesting. Otherwise, what did we learn from this? Well, there's this thing about being physically modular, about having abstractions. So how does that work for other kinds of robots? And well, we have the industrial robot that I talked about before. So this is a commercial video from Universal Robots. So that's a local Danish company that does industrial robots. They're doing really well. They started in our, well, almost in the basement in the lab in our university 10 years ago. And they've been doubling in size ever since then. And they were recently sold for 2 billion kroner, which is, well, somewhat less in euros, but still a lot of money. And I promised to tell them to say that they were hiring. They desperately need high-level software people. So they're doing really well. They're selling their robots all over the world. What's interesting about this robot is that if you look really carefully, actually, you can see it has these blue caps on the joints. So that's the exact same blue color we had on the ATRON modules, because these are the same people who made the ATRONs to begin with, who made that robot. This robot is actually highly modular. So the joints and the various segments are made, many of them are the same, and you have the same advantages in terms of making the robot easier to test, easier to make, and easier to produce. We do a lot of work with industrial robots as well. Currently, we're looking at how to assemble things. So assembly is something that robots traditionally have not been very good at. And it's, well, the thing is, when you have to assemble things, you have to sort of, well, there might be, imagine if it's a food processor or whatever for your kitchen. You want to assemble, well, the plastic parts might be a bit hard to get aligned probably. You have to insert screws and various other things. And well, it's a bit difficult for a robot actually, but that's something we are looking at the moment in research. And this brings me to a next thing that we picked up on from the ATRONs, which is, if you think about it, assembly might be an example of something that's interesting to be able to do in reverse. So that's what we're doing at the moment. So what we've done is to come up with a language for describing assembly operations, making robots build things that is reversible. So if you run the program backwards, the program will disassemble whatever the robot was building. So if you want to take your food processor apart for repairs, the robot now knows how to do that automatically. If you want to upgrade it to a larger motor or whatever you do with food processors, then it will do that as well. If in the middle of the assembly process, the robot gets stuck because of some misalignment, well, then you can back up a few steps and go forwards again, and that helps a lot. So taking this idea of forwards and backwards for the physical motions and putting it into language is giving us a lot of new possibilities for assembly operations. So that's something I'm working with at the moment, which I think is going to be really big. We have a nice sort of small domain-specific language. We have a try thing here, but it's not like a try-catch. It's try something a number of times, 3 times in this case. If it succeeds, keep going. Otherwise, well, if we fail more than 3 times, keep backtracking. So we have these constructs that are sort of similar but different. In terms of modularity, we're also working with agricultural robots. So the modules here are actually in the belts. So so you have this robot here, it's made by Concurrency, which is a local company, but in collaboration with University of Southern Denmark, has 2 of these modules, and we can use the same modules, the traction and battery and control, which is in each of them, for different kinds of implements. So we have again a reuse of physical pieces, and we can also reuse a lot of the programming. We're looking into domain-specific languages for expressing safety concerns, because these machines, I mean, this is like half a ton, so you don't want to get run over by it. Software is programmed in the thing called ROS, Robot Operating System. So I just want to mention it quickly, because if you want to hack your own robots, it might be a good place to look. This is not the official story, but to me, ROS is like the JavaScript of robotics. I mean, people who know how to do these things probably hate it, because, oh, this is terrible. But it's very easy to quickly put a lot of things together. So be careful. We also, so one of the keywords on the track was drones, unmanned aerial systems. I just want to mention that we're doing a bit of work there, but it's interesting, it's very difficult, very different from what we've been seeing so far. So we're looking at civilian applications, environmental monitoring, agriculture, and other things. But there's actually a lot of interest from society in working with us on this, because all of a sudden we have robots, unlike the robots I've shown you so far, which tend to stay put. Drones tend to fly out into the real world, and that makes things more complicated. So we're working with the Danish Transport Authority, Traffic Authority, on license plates for drones. So the police would like to know where is that drone right up there in the air from. So you want to hold up a tablet like this. And if it's unlicensed, then of course it's illegal, just like normal license plates. We have a local airport, so University of Southern Denmark is at Odense. And there's an airport there that was basically close to closing down, because they had a charter flight like a couple of times a week or whatever, which is not very much for an airport. So now they've converted the airport into a test center for drones. It's actually very nice. You can have a couple of square kilometers of airspace you can close off and test. So we have a drone lab there it's actually, so far it's been very useful, and we've been flying things and crashing them, and it's a good place to crash things, like over a city or whatever. And all kinds of other things that we are picking up on as well. A last thing, so many of the robots that I showed you before were kind of heavy. The same building kit idea also works for lightweight, energy-efficient robots. So of course, the heavier, the more massive the robot, the more energy it uses, which is bad. So here, this is a building kit for building completely different kinds of robots that are more springy, flexible, and much more lightweight, and that are orders of magnitude more energy efficient than the other kinds of robots you've been seeing. And the building kit idea here works for being able to experiment with it quickly. So again, we see the same principles, building kit, different kinds of parts being put together, occurring again and again. So even though the ATRONs that I showed before don't really do anything useful, we're seeing a trace of them in many places. So finally, robots, I talked about physical modularity, how it enables an incredible amount of flexibility. There's this cognitive gap, which is actually two ways. So robots have a hard time relating to the world because they only have limited sensors. That makes them hard to program. And we have a hard time dealing with how to program these things. And we need to do some more work there. And they're coming. They're becoming more and more useful, but they need your help. We need good software for the robots. Otherwise, it's going to be a disaster. DSLs, to me, they're the ultimate abstraction mechanism. I love them. But it's not magic. To get the right abstractions, to really get some punch in the language, it still needs the magic inside. And I don't know how to, I don't think we can systematize that. But we can make it easier to do good languages and not weird languages like, well, some of those that are out there. And this concludes my talk. And remember to rate the session. Thanks.
Okay, I think we have time for one question or maybe two. One is, how did you decide the shape for the ATRON robot or module?
That's a very good question. So I have to say that this is actually before I joined university, so I'm talking about other people's work here. I just did the programming. But there were actually, we do a lot of biologically inspired robotics, and so the inspiration for the ATRON was a cell, which was one reason for the round, combined with crystalline structure. So you want something that can fit into a grid, and something that can move easily around in the structure without bumping into other parts. And spheres are actually really good for that. So, and unlike many of the other modular robots that we saw, one idea in the ATRON is that it's okay that one module by itself can't do anything useful. In this case, it can just rotate in the middle. It can't move or do anything by itself. But then when you put many of them together, they can do something together.
Okay. One more. Actually, there are two about communication. What is the plan for scaling communications, handling bottlenecks and so?
So that's a very good question. In the work that I showed you with the ATRONs, it's highly scalable. And we've shown that also both with some larger physical experiments and some really big simulated experiments. Or scalable in the sense that if you're only communicating a limited amount of information, that information is communicated continuously, neighbor to neighbor, all the time, no matter whether anything new happens or not. So this makes the system very predictable. Almost, well, it's not actually real time, but it's sort of like something just clicking on, communicating information. And so long as the information we want to communicate fits into that, then we're fine. And then we could schedule different packets of information, maybe randomly or whatever, to be communicated at different times. Scaling up beyond that, that's actually some of the work I didn't show you. We have a notion of scopes of information. So here we're talking about a scope that's physically delimited. So maybe one end of the robot knows information that's limited to that physical scope, and another part of the robot has a different physical scope, and certain piece of information only gets communicated there. But this is where it gets really hairy, and so what happened with the ATRON robots is a couple of years ago we ran out of funding, and then we did a lot of experiments and broke all of the robots. And so right now, unless we get more funding, the ATRONs are sort of lying there, and we're not doing more experiments with them right now. Whereas some of the other robots that I showed you are easier to get funding for to work with. Robotics is kind of expensive to keep it going. So we have those distributed scopes sort of described in nice academic papers and simulations and a little bit of physical experiments. But I mean, to me, a motivation was always to make the physical robots that are sitting there in front of me do something new that they couldn't do before because I programmed them better. And that motivation is not there at the moment because they're all dead because we use them too much. But if at some point we get more funding, then we will pick up on these experiments. So to answer the question, I sort of got carried away. Physically local scopes, so bringing space more into the picture.
That's it. Thank you, Ulrik.
Right, thanks.